To close out this detailed lesson, we will cover arguably the most important and revolutionary aspect of Bitcoin and the blockchain, which is mining. But to truly understand mining, we must start with this portion of the compound, the blocks. Blocks are simply groups of several thousand Bitcoin transactions stored as separate files on the network. And the blockchain, hence the name, is a chain of blocks, forming a chronological storage mechanism that continuously builds on itself. These blocks or data files are stored on the nodes. Reminder, decentralized nodes are simply computers sharing files and data so that centralized servers are not needed. Instead of the blockchain's data files being stored on a bank's centralized server, it is stored in a decentralized manner across thousands of people's computers. There are four types of nodes: full nodes, super nodes, light nodes, and mining nodes. Full and super nodes store the entire blockchain, while light nodes store pieces of the blockchain, enough to validate transactions. And mining nodes are full nodes that also add blocks to the blockchain. Mining nodes are the only nodes that can add transactions. Not only do nodes store the blockchain, but as mentioned throughout this lesson to this point, nodes are what verify transactions upon the start. Since nodes store the blockchain and all its transactions, they have a full history of address inputs and outputs. When transactions are first submitted to the blockchain, nodes perform the verification process, ensuring no double spending takes place before the transactions enter the memory pool. Getting back to the blocks, let's dive a little deeper and see what actually goes into a Bitcoin block. We already discussed the transaction at the wallet and verification level, and now we will take a look from a miner's perspective. Quick note, a miner is a person or group of people with a mining hardware machine. Mining is the only human interaction needed to perpetuate and secure the blockchain. Each transaction that gets verified and approved is then added to the memory pool. From there, miners add the transactions to what is called a candidate block. A candidate block is essentially a holding block before miners officially add the transactions to the blockchain. The mining process begins when a miner hashes the transaction data to produce a transaction hash. As seen here on Bitcoin Explorer's transaction summary, each transaction has its own hash. This screenshot is taken directly from blockchain.com's Bitcoin Explorer, which tracks and shows every single Bitcoin transaction that is ever confirmed. Every single transaction that is added to the candidate block is hashed in this manner. From there, each transaction hash is hashed together to form what is called a Merkle tree. The Merkle tree results in one Merkle root hash that represents all the transactions within the block. Let me show you what I mean using the hashes from the previous slide. Each transaction had its own hash, as shown here, 4 different transaction hashes. From there, I hashed these 2 transaction hashes together. As you see here, 8 or A84B, A84B, etc. Hashed with 7D06, hashed with 7D06. These hashes come together to give me 87D, etc., etc. Same thing happens on this side. These 2 transaction hashes are hashed together to give me this summary hash. Then these 2 hashes are hashed together to produce this summary hash, which is called, again, the Merkle root hash. The Merkle root hash is a summary hash of each transaction within that block. Do you remember this screen from a previous lesson where I showed you the input that I use to get specific hash outputs? Well, it's important to note that the Merkle root hash of a candidate block or a confirmed block is unique to the specific transactions included in the block. Since the hash output is a direct cause of the specific input used, whatever transactions the miners select for their candidate blocks directly impacts the transaction hashes that go into the Merkle root hash. This is an important concept because once a block is confirmed, it cannot be tampered with in any way, because any attempt to add, delete, or modify its transactions would result in a different Merkle root hash than what has already been accepted and set in stone. If a hacker tried to change one transaction within a confirmed block, it would change the hash of that transaction, which would make its way up and change the Merkle root hash completely. And any attempts to change what the blockchain has already accepted will be denied by the blockchain. This is an important concept in regards to preventing double spending and securing the Bitcoin network. Once the blockchain confirms transactions and confirms the blocks, those things are set in stone, and the blockchain views them as how it should be. So any attempt to change anything gets denied and essentially discarded. Now that you understand Merkle trees and Merkle root hashes, we will discuss another key aspect of mining: nonce. So let's say I'm running a nonce lottery where I announce a starting and ending number and a mathematical operation that must be used to determine the hidden nonce number. Obviously, you could just divide B by A. So let's say in this world, division doesn't exist at all, so it's not in your head and it's not on your calculator. So the only way to find out what the correct nonce is to multiply A by random numbers until you eventually land on B. Now imagine it's you versus thousands to millions of others, and you are all trying to find the correct nonce because whoever wins gets a big reward. So let's say you get lucky and you're the first person to discover the right answer. After countless trial and error attempts, you tell me the correct nonce is this large number here. After I calculate it, I say congrats, that's correct, and I hand over the money to you. Then the lottery starts over again with new numbers. For example, A equals 2.58 and B equals that extremely large number there. So again, your job is to find what is the random number used that was multiplied by A to end at B. So a different person now sends me their answer. I check it and I say, congrats, you're correct, and hand over the money. Makes sense, right? Nonce is just a random number used once to solve a problem. But with Bitcoin, it's not as straightforward as simple multiplication with big numbers. With Bitcoin, it's all about hashing. So the nonce gets hashed with other components to arrive at the target number, similar to that lottery system that I just went over. But let's rewind a little bit and talk about Bitcoin block headers. Each block contains a block header consisting of the Merkle root hash, the correct nonce for that block, and a hash of the previous block header. Those three things, plus other things, are hashed together to formulate an overall block header hash that acts as the master fingerprint for each block. Since each block header contains the hash of the previous block header, the blocks are chained together, and each new block relies on the data of the previous block. This means that any attempt to change a transaction that has already been confirmed will result in a changed Merkle root hash, which would result in a changed block header hash, which would change the starting point of the next block, changing the necessary nonce, and so forth and so on. Remember, once the blockchain confirms a block, it's set in stone and it only understands the data in the context of what was already approved. Changing one transaction would set off a chain of changes and errors that would result in a completely different blockchain. This is a key element to the decentralized blockchain being able to secure itself. This is also how forks are formed. Essentially, a fork is the rules changing or a hacker coming in and attempting to redirect the blockchain.